Hi there, so this is part 2 of lecture 21 review of eigenvalues and eigenvectors. Okay, so let's begin some examples. So we have seen how to compute the eigenvalues and the eigenvectors, so let's run some examples, right? So first, a really nice symmetric matrix, A equal this one, okay? And now we're interested in the determinant of the A minus lambda I. It has to be 0. So let's do them. So let's first find the eigenvalues. We want to compute the determinant of this. So we have this times this. We have 3 minus lambda squared. And then we have minus 1 here. So there we have lambda squared minus 6 lambda plus 8, right? Yes. And then this can be factored out to be lambda minus 4 lambda minus 2. So you have the lambda, the eigenvalues, which are the root of this equation. They are lambda 1 is 4, lambda 2 is 2. Okay, so that's our first step. Find the eigenvalues. So evols, I'm going to shorten it out by writing evols as an eigenvector, eigenvalues, and effects as an eigenvector. So the second step here is to find the effects eigenvectors, and we have to do them manually one by one. Okay, so for each eigenvalue, so the first one is 4, we plug it in here. So we have 3 minus 4, and this is 1, 1, 3 minus 4 minus 1. So x equals 0, right? Because remember, we're interested in the complete formula for this is the we begin with this term, right? This term right here, a minus lambda I x is 0. So we are plug the lambda back here, and then we want to compute the x. So here we can find the eigenvector, the first eigenvector, which is 1, 1. And then for lambda 2, which in this case the eigenvalues is 2, can say 1, 1, 1, 1, 1, and we're interested in the x, and we know it will be minus 1, 1, or even 1 minus 1, it doesn't matter. It's just a line along that solution. So that's it for this example. And the first example, this one is actually the first case, which is the symmetric case. So symmetric case has a unique solution of the eigenvector, which the eigenvector will be perpendicular. This is my symbols for perpendicularity, or as we learned in the previous chapter, orthogonal. So how do we test if they are orthogonal? Simple, we just dotted them, and they must be 0, right? So 1 times minus 1 plus 1 times 1, of course it will be 0. You remember the dot product is like the element wise, so this times this plus this times this. Okay, so they are 0. So yep, the eigenvectors of the symmetric matrix are perpendicular. So that's the first fact, and let's move to the second example. So my second example is one that actually covers matrix model 1, 2, and 3. So these 3 case of matrix. So this is our beautiful matrix. So first, there's a matrix called a Markov state, which state the probability of one event in each component. So that's what it means here. The Markov is the case where the sum of each column equals to 1. So 0.5, 0.5, 0.5, 1. So it is guaranteed that it has the eigenvalue of 1. So the eigenvalue of 1 is one of the eigenvalues, not all, but one of them. Okay, is an eval. And the same thing as here, this is also singular, right? If you see that these are the same rows, and of course they're singular matrix, and it is guaranteed too that the one of the eigenvalue is 0, because this is the case of singular. And also, of course, this is if you transpose this and it will stay the same, so this is also symmetric metric. So you will know that you will see later that the eigenvector will also be perpendicular to one another. So let's solve this. So we can follow the previous formula, like we should remember it by heart now that we're interested in determinant of this matrix. And then I'm not gonna compute it, so you can do it yourself. I encourage you to do it on your own. And the result is that the first eigenvalue is 1 and the second eigenvalue will be 0. Okay, and this is actually fulfills these two criteria that we have here, which are the Markov and singular have these two eigenvalues, and it just happened that we have the 2 by 2, so each case of eigenvalues fit perfectly to our criteria. And the eigenvector is 1 1 and also -1 1. And you can see also here it satisfies our first criteria, which is a symmetric matrix has the perpendicular of eigenvectors. So let's move on to the next example. So let's go to the example number 4, which will satisfy our criteria here. So this is the reflection matrix. This is an example from the book, and I will not compute it as thoroughly, so I'll just show you the result here. This is the first one, and this is the -1, the eigenvalues of them. Please compute it yourself to confirm. And the eigenvector is also 1 1 and 1 -1. And then I write some information here that shifted by identity, no change in eigenvector. And that's also the reason why I wrote the first two examples here. You know, this first one, the symmetric matrix, and the second one, which fulfill the symmetrics, Markov, and singular case. What similarities can you find in these three examples? So you will see that the eigenvector of all those matrices are the same. Okay, so why that happens? That because actually this matrix, let me call it A1, let me call it A2, call this A3. So what is the relation between A1 and A2? Sure, I can just subtract the 4 of identity from A1, right? Then I will end up with A2. So 3 1 1 3 minus the 4 4 0 0, then I have this one, right? So this is A2. And what about I3? The same way, I can go from A1 or I can go from A2. Let me go from A2. I'm terribly sorry, I just find a really terrible example here. This is not the correct matrix that I showed you earlier. It should be the Markov one. So 0.5, 0.5, 0.5, 0.5. Therefore, a way for me to get from A1 to A2 would be first to subtract not the 4 but the 2, so that I have 1 1 1 1, and then I can multiply them by some scalar of a half here. So this will give me 0.5, 0.5, 0.5, and this is A2. And this matrix, how do I get A1 from A2 is by shifting A1 by this vector, right? And then I just multiply some scalar. So in the end, I'm just shifting by identity. The same thing happened if I go from A1 to A4, for example. In this case, it's pretty straightforward. I can just subtract the 3 identity from A1 to get into A3. I still get there. I'm pretty sorry for the earlier example. So you can subtract this and you will have 0, 1, 1, 0, which is the A3. So all these metrics are related by only like shifting that information in the identity part, you see. And this is a really unique information and really important one, that shifting by identity, there's no change in the eigenvector. See, all of them has the same eigenvector. You only need to concern about how it will change in the eigenvalues. So let's go into some more examples in the next video. Thank you.